All right. If not, we're gonna continue our discussion. What in lecture 23. Today we're gonna discuss um cross sections and decay rates. So let me start by a summary of lecture 22. So this was a lecture I decided to add. Originally, I didn't want to discuss these, but I thought for sake of completeness, I should have it. And then I also went over LSC very fast. So LSC, I went over LSC very fast and word identities very fast. We're going to come back to that and do a proper job, but not today, right? So today we're just going to discuss cross-section and decay rates. It is a lengthier topic than what fits inside one lecture, so I will suggest side readings. You will have to do the homework to get a sense of it because it's a lot of calculation steps I won't have time to reproduce on here live on Zoom. But anyway, so summary lecture 22. In the previous lecture, we discussed an example of a Yukawa amplitude. So these are examples of Yukawa amplitudes. So for example, fermion anti-fermion scattering. So there were two diagrams contributing to this. This is a fermion, this is an anti-fermion, this is some fermion propagator. The vertex is minus IG, right? Gamma mu, right? Sorry, it's minus IG. It's not a yeah, it's just minus IG. And then this is V bar of S, V bar of S of K. Sorry, I had made a mistake here. So V bar of S of K for this guy, and U of P for this guy. So these are the two fermions here, right? And then this is the propagator for the fermion in the middle. And there are two terms here. There is the plus that we add them together. Why is that? Do you guys remember why we added them? It's because the final states are bosonic, so they satisfy the commutation relations. So the wave functions are symmetrized. We said that we have to square the amplitude to calculate something like cross-section. But before even talking about what cross-section is, or reminding you guys what cross-section is, because hopefully you've seen cross-section in advanced quantum mechanics, you should know that just from Born's rule, the raison d'etre of amplitude is to be squared to give you probabilities, right? So probabilities are the things that are going to go into observables, things that we observe. So there's always these S and S primes, right? The spin that correspond to the initial and final initial states, right? In this case, right? Because initial states are fermionic. And we're gonna always average over these spins, right? Because just assuming that we don't really know what the initial spins are, we're gonna average them. There is S and S prime dependence here that I usually suppress to keep the equations clean, right? What we did was that squaring the amplitude using we wrote it in this way by just organizing these matrices, right? We wrote it as a trace expression. Here are the two fermion propagators. These are 4x4 matrices, right? This is P slash plus M. This is a 4x4 matrix, right? If you recall, P slash is P mu gamma mu. Gamma mu is a 4x4 matrix. And M here means M times identity, right? Here are here's another, the two other propagators and, oh, sorry, I'm missing yeah. So there in the amplitude we had SF plus SF of P minus P prime plus SF of P minus K prime. So this is, I factored them out. There's a plus sign here, right? And then these guys, I've arranged them around in such a way to contribute to a 4x4 matrix. This is sort of like the contribution of M, and then there's a well, it's actually not true. So there's U, and the part of this U half of this comes from this guy M, and half of it comes from M star. So you rearrange them in the form of a trace over these 4x4 matrices, right? So far, so good. Okay, then we said that, well, we could simplify these because these 4x4 matrices are basically a bunch of Dirac matrices, right? So these are, every time you have slash, you have gamma matrix, right? And there are the simple identities to use is that the trace of an odd number of Dirac matrices vanishes. Two Dirac matrices, the trace of them is 4 Adam Unu. That's just trivially follows from Dirac algebra, right? And 4 of them, there is this relation that you could obtain, right, by recursively using the anti-commutation relations. All right, so these are identities that you use to simplify expressions of these type. Keep in mind that this is just a sample calculation. Quantum field theory is full of such calculations, and it takes some getting used to, but this is why you, yeah, have homework. We discussed Feynman rules for QED. Whoops. We discussed Feynman rules for QED. So for QED, because we haven't quantized a gauge theory yet. So in QED, you have fermions that are and coupled to a U1 gauge field, right? We haven't quantized photons yet, but I just gave you the essential, very basics of how it works. You're, of course, going to end up with this photon propagator, which is the time order 2-point function of a mu vector potential, right? And we call this I delta mu nu x minus y. This is a photon propagator. And it's basically like a propagator in the Feynman gauge, right? It's a gauge theory, right? In the Feynman gauge, it looks like the propagator from massless fields, but a 4x4 Adam mu nu matrix worth of it, right? And that came from the fact that in the gauge we're working with, the equations of motion were basically this, right? So they look like 4 copies of massless Klein-Gordon equations. All right. We discussed the issue of negative norm states. We said that's unphysical, and gauge theory, quantization of gauge fields basically guarantees that those go for the right. They never contribute to any observables. And if you recall, this whole thing is this whole extra junk we've introduced, redundancies we've introduced, gauge degrees of freedom, is because we want to insist on a local action, right? So what would go wrong? Where in quantization are we using locality? Does anyone, do you have a guess, thoughts?
That's why the entire reason why we're introducing the gauge fields, right?
Yeah, so
to maintain locality.
Yeah, no, that's right. But let's say scalar field. What would have been different if our scalar Lagrangian were not local?
You couldn't just like integrate it, and you wouldn't have a density that you can just integrate over all x.
So yeah, very, very, very good. So let's just first say it was local in time, but non-local in space. That would mean that in your action, in your Hamiltonian, you would have phi x, phi y's instead of phi x squareds, right? This would mean that a mode K would propagate and could go to turn into mode K prime, right? So your propagator wouldn't be diagonal in momentum basis, right? That would be crazy, right? It's just because if things were non-local, AK and AK prime, AK and AK prime dagger would acquire a 2-point function, right? Because the Fourier transform of x and y, the Fourier transform of phi x squared is the thing that gave you phi of k, phi of minus k, right? Good. Anyway, so that's just a side comment. Okay, asymptotic states of photons. I just told you what they look like. These are polarization vectors. And then I said the electron photon vertex is minus IE, electric charge, or if you have a fermion of charge Q, here you would put Q, gamma mu, right? Now, in the next part of the course, starting next lecture, we'll actually derive these rules. We'll discuss this in full detail, but for now, because we want to do calculations, sample calculations of amplitudes, I just give them to you. Good. We talked about the electron scattering in QED. There were two diagrams that were contributing. There was this diagram, and then there was this diagram. There's a relative minus sign, and that could be explained using either anti-commutation relations of fermions, the fact that they have their statistics, right? Or the fact, or Pauli exclusion principle. These are the same things, right? We discussed Compton scattering, which is the scattering of a photon from an electron. There were two diagrams that contributed. Here, there was the first diagram, the first process we discussed that had an external leg that was a photon, right? Up to here, in the first example, photons were internal stuff. So here, photon is an external leg. And then because in your description of external particles, you're dealing with the gauge theory, there's one extra condition. It's called Ward identities. It's a consequence of the conservation of current. It basically says if you have an amplitude that takes m particles and takes it to go, n particle come in, n plus one particle come out, for instance, it could be and one of them is a photon. Here in this example, photon is an external final state. It could be an external initial state. If you have a photon, either in the initial or final states, this guy, if you contract it with p mu, this will vanish. Right? So that's the consequence of conservation of current. I just said it, but we didn't discuss this in depth. I did not explain this well. Clearly, I'm going to come back to this and discuss this properly in the next part. All right. So that was a summary of what we discussed yesterday, last lecture. Any questions about last lecture? All right. Today, what we're going to discuss are decay rates and cross sections. So what is the story? For simplicity, let's assume we're considering the following processes. You have some sort of amplitude. The simplest case is where the incoming particle is a single particle, right? So all that can happen is that either the single particle propagates or it decays to something else, right? So one particle coming in and a bunch of outgoing particles, that is the process for which we have to calculate decay rates because the particle is unstable and decaying, right? If it were a stable particle, it would be just propagating fine. Then the other process that we consider is that if there are two incoming particles come and scatter and turn into n particles, we often, even though today I'll make some comments about 2 to n, we often focus on the 2 to 2 scattering, right? That's a simple setup. Two particles come in and two particles go out. That is the canonical case that you should have in mind, right? A lot of intuition is built on 2 to 2 scattering. When you focus on 2 to 2 scattering, you see that just from the kinematics, from Lorentz invariant, Poincare invariance, you learn that they're basically your amplitude, your cross-section, your amplitude, all of that is basically characterized in terms of three variables. We call them Mandelstam variables, S, T, and U. They're convenient variables, and the 2 to 2 scattering is just characterized by these variables. We'll see that. It helps us actually organize Feynman diagrams. We will discuss how cross-section could be calculated from the amplitude. There will be parts of the argument that I'll just refer you to, Peskin-Schroeder and Schrednicki. But I'll try to sketch the whole argument, but just for the sake of time, I'll have to refer you to parts of it over there. So section 4.5 of Peskin-Schroeder and section 11 of Schrednicki have an extended discussion of this. All right, so that's what I want to do today. Any questions? How many of you guys have seen resonances in quantum mechanics before? Well, I guess there are only a few of you guys. I see only a few of you guys have videos on, so this is not a very helpful All right, that's fine. So I'll try to explain it, but if very briefly, but if you haven't seen it, there's plenty of deep physics in resonances. We'll discuss that when it comes to decay rates. But before talking about decay rates, let's just focus on 2-to-2 scattering for now. And in particular, we're going to focus on Compton scattering. What was Compton scattering? It was a scattering of E gamma to E gamma, right? Photon electron scattering. It's a very, very common process. It's just turn around, everything around you is photon electron scattering. Like, it's absolutely surrounded by it. You can't take a break from it. The whole universe around you is this Compton scattering. All right, so here are the two diagrams that contribute to it. Right, let's go slowly. So here's this diagram. There's an external photon, epsilon mu of P. There's an external the photon in the final state, epsilon mu star of P prime, right? Then you have the U bar of K prime. That's the electron, that's outgoing electron. There's an incoming electron. The two vertices will contribute gamma mu, gamma nu minus IE squared, right? There are two copies of it, the vertices. And then here is the propagator for the intermediate fermion, in this case, Q, and in this case, Q prime. So how do you find Q and Q prime? Just conservation of momentum at each vertex. So the amount of momentum that flows in here, right? In this vertex, K plus P come in, 4 vectors come in, Q has to go out. So Q is P mu plus K mu, conservation momentum. And here, there have two relations. So this also relates to final and initial states. Q prime here is clearly yeah, okay, I've written this one down. K prime is equal, K prime minus P prime is Q prime, right? Q prime plus P is K prime minus P is Q prime. Good. All right, so let's call this diagram MA, this diagram MB, and just I'm going to keep the E squared outside, right? Just some on-shell conditions. We said in the previous lecture that if you use on-shell conditions, because these external legs are on-shell, right? You could use them to simplify these expressions in this form. I'll not reproduce this again. These are things that you will do your homework. You'll work out in your homework. And then after doing some Dirac algebra, you find that, for example, this first term squared, the norm of this term could be written in the following form. So all these expressions are in terms of the dot products of P and K, P prime and K, right? And K and K prime. Now, we introduced the following three variables. They fully characterize the 2-to-2 scattering, any 2-to-2 scattering, actually, even if the masses are different. But for now, we're talking about Compton scattering, right? It's P plus K squared. We call it the S variable. This is the center of mass energy, right? It's sometimes called the invariant mass. You could write it in these different ways using conservation laws. You could define the T variable, which is Mandelstam T variable, is K prime minus K squared. This is the square of the form momentum transfer. So let me draw this picture so that you guys have this in mind. Right? So P plus K squared, this guy, is the center of mass energy. It's the initial center of mass energy. This T is K prime minus K. This is square of form momentum transfer, right? It's clearly related to P prime minus P by conservation. And then U is P prime minus K. So it's like kind of diagonal. Now, these are three Mandelstam variables, and you can prove that the 2-to-2 scattering could be always characterized in terms of these three variables. You'll work out in your homework that they satisfy this nice relation, that S plus T plus U is 2m squared, so they're not independent. They're really two of them are independent. All right. Now, just using the rest is Dirac algebra, and squaring things, we write down MA squared in terms of S and U variable, right? So I've written in terms of S and U variable. Now, MB, so if you recall, let me bring it back. MA and MB, yeah. This is MA and this is MB, right? The thing that's happened is that how do I go between the two? P goes to minus P prime, right? Look at this. So if I call this P prime and call this P, and this minus will change the flow of it, direction of flow of it. This could be thought of as a final state, and that could be thought of as the initial state. But you could also check explicitly inside the expressions that sending P to minus P prime gives you MB, takes you from MA and to MB. That basically swaps S and U variables. So you could write MB in a nice way. So there's MA squared, MB squared, and then you calculate MA star MB. These are three expressions you could write down. This is just check that you could always write them down in terms of S and U and T. Here I've written them only in terms of S and U, but of course S plus T plus U is 2M squared. So I could have written it in terms of T as well, right? There are only two variables that are independent. If you average over initial spin, it gives you half squared, 1/4. I leave that to you guys to figure out why. Finally, quarter of sum of M of A squared, right, is basically sum of MA star MB, MB squared, MA squared plus MA MB star, right? You put them all together, and this is the expression you find. One thing to notice is that these U minus M squared and S minus M squared make an appearance, right? So that's not terribly surprising because S minus M squared is this dot, right? And T minus, U minus M squared is this guy, right? So what is nice, often you see that when people discuss scattering theory, there's a grand theory called scattering theory, or that there's a whole approach to quantum field theory based on scattering theory. And it's based on the idea that actually if you work with cases where masses are zero, then these end up being really nice polynomials or like some nice expressions in terms of S and T and U. I'll not further comment on this. I just wanted to say that there are these nice expressions and they have very nice symmetries actually. Yeah, I will not mention the symmetry. There is something really neat about this expression. Well, actually, I will make one comment about it. So this is the answer that we found. In general, in any 2-to-2 scattering, that's like P comes in, K comes in, P prime goes out, and K prime goes out. There are three channels that contribute. There are three diagrams that contribute. There's this diagram. I haven't specified what is the thing that's propagating, right? It could be a fermion, it could be a boson, it could be Yukawa theory, it could be QED. There's this guy, there's this guy, and then there's this guy. This is called S channel, this is called T channel, and this is called U channel. And it's pretty clear that to go from the expressions from this diagram to this diagram, all you have to do is that you have to swap send S variable to T variable. To go from this to this, you send S variable, you replace S variable with U variable, and so on and so forth. So there's a really nice picture for what's the role of these variables, right? Yeah, do I want to say anything else? Any questions? Any questions? It takes some getting used to, but these Mandelstam variables are a very helpful way of thinking about organizing our minds. Just recall that S is called invariant mass, or it's basically square of center of mass energy, right? So that's very, very physical. Good. So because these scattering processes are Poincare invariant, you could always go sit in center of mass frame, right? So square of center of mass energy is a very physically relevant quantity. That's S variable. The T variable is the force momentum transfer. Well, I leave that to you guys to figure out. Perhaps over explaining. One thing to keep in mind is that the dimensionality of S, T, and U are mass squared, right? So they have the dimensionality of energy squared. So it's square root of E that has dimension of energy, square root of T that has dimension of energy, and square root of U that has dimension of energy. All right, any questions? A little bit more about cross-section. So what is cross-section? This is just a reminder, and this discussion, you could read it completely, fully in section 4.5 of Peskin, 5.4 or 4.5? Anyway, 4.5, I think, of Peskin. What we observe in quantum field theory is we take a bunch of particles, like beam of particles with many particles, and another beam, and just collide them head to head, and a whole bunch of stuff come out, right? Like a whole bunch of crap come out. And the way that we study this is we characterize the beam that we have in terms of the density of particles of type A. So it's a beam of type, a particular beam, it has type A particles, it has some area. The density of particles inside the beam is something that we do know. And the beam is just like, it has a length, right? Or we have the beam for a short amount of time. It's moving with velocity v, right? VA, and it lasts for some time TA, right? So what you can imagine is that you have a whole bunch of particles with density rho b, and they're moving with velocity v, right, in this direction. And then you could talk about the beam lasting for some amount of time, or you can talk about the length of this beam, right? They're the same thing. They're related by velocity. So those are the things that that characterize our initial beam. Same holds for another beam, and we collide them head to head. We could sit in the center of mass frame, or another convenient thing for scattering theory is to say that rho A particles are at rest and rho B particles are just approaching them with velocity v. Right? These are two different frameworks. So what do we observe? As we collide these two beams, we can count the number of scattering events, right? We have our cloud chamber, or whatever is our detector. At Geneva, we see a whole bunch of new particles. We can count the number of events, certain number of fermions or final states are produced, and we detect them in the lab, right? We can track them down. So the total number of scattering events is, what is it proportional to? You expect it to be proportional to rho of A, rho of B, area of the beam, and the length LA and LB, right? So you expect them to be proportional to all of these guys. So we define the cross section as to any particular final state to be the number of scattering events to that particular final state divided by rho A, rho B, LA, LB area. Of course, this area is the area of the overlap of the two beams. If the two beams miss, yeah, we've got nothing, right? It's about how much effective overlap they have. Now, I'm oversimplifying the matter. A beam that you create, it doesn't have density that is like uniform. So the density could depend, actually in reality, the density depends on the point. So these are all like, this is not a division. There is like, you divide, you sort of like take an infinitesimal point, right? You take this to be a teeny tiny point, and then you divide it by infinitesimal elements of it, right? You take derivatives. But for for the purpose of our conversation, it won't matter. We're not experimentalists today. I'm not experimentalist, period, but some of you guys might be experimentalists. Good? Any questions about this? So that's what the cross-section is. It has a dimension of area. Now, we're often interested in final states with fixed momenta. That's what we've been calculating, right? We've been calculating two particles of fixed initial momentum come in, two particles of final fixed momenta come out. Initial momenta, we prepare them in the lab. We prepare these beams with fixed initial momenta. So we would like to know what is the cross-section to final states of particular momenta. So we define, for that purpose, we could, if we don't fix some final momenta, what we get is called total cross-section, right? But if we fix the final momenta, what we call is a differential cross-section, right? So final momenta, even we can never really fix them to be sharp. We say we divide them by some small interval for P1, some small interval for P2, P3, all the way to Pn. Let's say I collide two particles and n particles come out, right? This is called a differential cross-section. And once you integrate over all the final momenta, you obtain the total cross-section. An important point is that the final momenta are not constrained because of conservation laws. So this whole business is somewhat more tricky, right? Let's focus to see how tricky, why is it tricky and how does it change? Let's focus on 2-to-2 scattering, right? How many variables do we have in the final? So P mu and K mu, the incoming things, we have fixed them. We have prepared beams of particular P mu, particular K mu. That's fixed. All that's left is P prime and K prime. These are on shell. Each of them is a 4-vector. So each of them is a 4-vector, but they're on shell. So each of them has 3 degrees of freedom. The on shell condition kills 1, right? So 2 times 3, there's 6 variables in here. But we have 4 conservation laws, right? The sum of these 2 should be equal to the initial things. So out of the 6 degrees of freedom, 4 conservation laws kill 4. You're left with 2 final degrees of freedom. There are various ways to use Poincare invariance to label these, to change these variables, to use different parameters to parameterize these variables. One way that we often use it is we pick this to be the theta and phi directions of the momentum of one of the final particles. So there are 2 particles that come out, right? Now the 2 particles that come out, you can think of the first particle, the momentum of it in the z direction. The other vector is a vector on sphere, right? Making some particular angle with this, right? So to define that point, you can use it using theta and phi variables on S2, on a 2 sphere. And then if that's the way you think about it, the differential cross-section could be understood as d sigma d omega. D omega is just a unit element on 2 sphere. If this was fast, hopefully your homework will push you to work through this. Any questions about this? It's geometry, it's kinematics. There's no deep physics going on here, it's just kinematics. Do you guys know what the distinction, what a physicist means by kinematics versus as opposed to dynamics? Well, okay. Let me not go on tangential directions. All right. So that's what the cross-section is. And I just explained a little bit more about it. Let's put this on hold. Let's go back to decay rates because decay rates are easier to explain. Then we come back to cross-section and finish that story, explain that story a little bit better. Any questions about this for now? So far I've explained what the cross-section is, the definition of it, and what is a differential cross-section. It's just these are definitions. Good. All right. So decay rates. Decay rates are when we're talking about the process that, say, for example, one particle comes in and a whole bunch of them go out. this actually decay rates are not just relevant for this. Decay rates are relevant for all sorts of diagrams, right? For example, you could create, so far the particles that we've been discussing that we create that propagate in between in our diagrams, they were all like stable particles. They were not decaying. Electron was stable. In the electron-positron scattering, right? Electron was propagating, but that particle was stable. Or photon, when you two electron exchange a photon, that photon is a stable particle. So how does it change when the particle is not stable? So what we usually can calculate in a setup like this is decay rate. It's the number of decay per unit time per the number of A particles present. So let's say this is the A particle, right? The number of decays per unit time per the number of particles present. That's a very obvious quantity. Now, so there could be many decay channels. The particles can decay to, I don't know, 2 photons, could do, well, to a whole different set of particles, right? Each of them we call a decay channel, right? So each of them will have a decay rate. And what we do is if we sum over all these channels, what we obtain is the total decay rate. The inverse of the total decay rate is called lifetime. Right? Okay. So again, these were some definitions, but should be familiar, hopefully, from earlier physics you've learned. But now the connection between decay rate, unstable particle, resonances, and decay rates. There is this thing called the Braid-Wigner formula. I'm going to try to explain it. Let me say it in words before talking about the setup here. In scattering theory, no, actually, this is a good saying it. So in scattering theory, we saw that we had propagator we had the propagator, right? The poles of the propagator, we interpreted them as particles of a particular mass, right? Stable particles, particular mass. So you took the propagator, you went to momentum space. The propagator for free bosons was 1 over p squared minus m squared. We said this pole, p squared equal m squared, is a pole. And we interpreted that as a particle of that mass. We saw that these poles shift under interactions, and we called that renormalization of mass, right? Mass is corrected, right? By the way, do you have an intuition as what renormalization mass is? If a particle is propagating, right, in some sort of medium, let's say you have a boson propagating, and in the medium, it's propagating in a medium that's full of photons, for example. I don't know, right? Those diagrams we were calculating that corresponded to shifting the mass is sort of the effect of this medium on how it slows down the propagation of this particle. It changes the mass, right? Yeah, I'll leave it at that. If the medium and the particle don't propagate, don't interact, it just cruises through it, right? So there is no correction. But if they interact, that could slow down their process, right? And that is like, you could interpret that in relativity as shifting the mass. Anyway, all right, so back to the topic. So you look at the 2-point function, right? In the momentum space, the poles of the 2-point function are stable particles. We saw that when you took the 2-point function and separated the 2 points time-like separated for times much larger than inverse mass of the particle, the 2-point function just oscillates like e to the power of imt or minus imt. I think my notation is minus imt. All right, it's just oscillating in time. Now, if this were an unstable particle for long times, you expect it not to just oscillate, but also decay like e to minus IMT minus gamma t. Gamma is the decay rate. You expect the 2-point function to decay. All right, good. And this step function, this the Heaviside step function is the thing that we needed always. I didn't write it here explicitly, right? So if you take this expression and Fourier transform it, and you're just careful with your relativity, right? You keep track of everything. You realize that the Fourier transform of this is the following propagator. It's 1 over p squared minus m squared plus im gamma. So this rings a bell, hopefully, from our discussions before. This looks like the I epsilon prescription, right? So one way of describing the I epsilon prescription is that you could think of it as making your propagating particles a little bit unstable, a teeny tiny bit. How did we achieve that? How did we come up with I epsilon prescription? If you recall, we shifted t, we gave t a tiny imaginary part, or we made that made the Hamiltonian. Yeah, well, okay, I'm over explaining. Anyway, all right. So this is the propagator for a particle that's unstable, and then this is the decay rate. So we said that the well, for this, if you take the cross section in the calculation of cross section, m squared comes in. So it looks like this. So if you square this guy, you're going to get 1 over p squared minus m squared plus m squared plus gamma squared. So if this were a sharp pole, in the cross section, you would see these Dirac delta functions, right? But when it's unstable, when you plot cross section as a function of energy, you observe that this is like a peak with some width controlled by gamma squared. I'm just literally plotting functions of this type. And gamma controls the width of it, and of course the height. Right? So when you look at some sort of cross section, you plot cross section as a function of energy, right? If you see a Dirac very sharp peak, incredibly sharp peak, like Dirac delta function, that is a stable particle. When you see a peak that has some width, that's an unstable particle. That's called a resonance. It could be interpreted, as we've seen before, as a pole in the 2-point function off of the real axis, right? This is a pole off of the real axis. In the I epsilon prescription, we shifted the poles. One way of thinking about it is we shifted the poles above and below in the Feynman propagator, right? This is actually how we discover particles in colliders. We plot cross sections, and if there is a bump somewhere, this is if we can go look up the discovery of Higgs, all these particles, they're always these beautiful plots, and if there's a bump somewhere, that is the sign of in some cross section as a function of energy. That's a sign of a resonance. That's an unstable particle, and then from the width of it, we read off the lifetime. Good. So the fatter it is, the faster it decays, right? So that means that if you have a very, very short-lived particles, you see a teeny tiny bump. It's barely a bump. It's like coming down, and there's like something like this. If it's a very, very short-lived particle, right? Any questions? This whole like resonance theory of resonance is a beautiful story. In quantum mechanics, quantum field theory, this is all I wanted to say about decay rates. Now we're going back to cross section. Maybe I should have ordered this differently, but so going back to cross section. All right, actually, let me pause for a little bit longer. are there any questions about unstable particles, decay rates, resonances? So resonance is basically these poles off the real axis in the 2-point function. That's what the resonance is.
So the sign of the I
There's
epsilon
a
is
fully non-relativist. Oh,
actually
by the way, this I did not explain this. So this Braid-Wigner formula is a well-known formula in scattering theory and quantum mechanics, right? Which talks about the shift of in the propagator and its relation to resonances. And this what I just discussed is the relativistic version of it. Higher dimensional quantum field theory relativistic version. So you could look it up, read about it, and learn more. So back to the cross section. What we're going to discuss is kinematics. So, oh yes, is there a question? Yes.
Yeah, can you hear me? Hello.
Sorry, is there a question or?
Oh, can you hear me?
I cannot hear you.
Mm.
Can you guys hear a question?
Can you hear us?
Oh, you can hear him. Uh-oh, something is wrong. Sorry, can you ask again?
Testing.
Oh, I'm
Are
sorry.
you audible?
Okay, I can hear now.
Oh, great. So the sign of the ISO prescription is actually related to the decay rate, right? That I
So I just made an analogy between I epsilon prescription and decay rates. I epsilon prescription was just some trick, mathematical trick for time ordering, right? Here we're dealing with actual physical decay rates.
Okay.
Yes. Okay.
Yeah. So when we are doing ISO prescription, the actually sign of the epsilon is important, right?
Absolutely.
So
It's about the sign of the epsilon is about whether we close the contour above or below.
So is this related to the positiveness of the decay rate or?
Yeah, that's for sure. Yes. So in the analogy that I made, which was that I was describing the connection between epsilon prescription and decay rates, right? If you want to follow that literally, you realize that the sign, of course, is very important. This gamma has to be positive, right? If gamma were negative, this would be a growing mode. Right. But this you usually realize it has to do with the fact that, like it has to do with time reversal, right? Decaying mode is time reversal asymmetric. Right. So it's a little bit more nuanced. And the same way that the 2-point functions we're talking about that were retarded or advanced, they're time reversal asymmetric, right? So there is just some Fourier transform properties you have to be careful with, but the analogy holds.
Okay.
Did I miss any other questions? Somehow I couldn't hear you guys, oddly. No? All right. Sorry about that. Somehow my headphones were useless. Was there another question? Okay. All right, back to the cross section. I think I should speed up because so consider that we have some initial state. Phi A and phi B are two beams of particles of A and particles of B, right? And we want to calculate the probability that these initial states scatter to some final states of n other particles. So this is the probability of A and B beams going to 1 to n, right? Of course, the n final particles can have different momenta, and the total probability you have to integrate over their momenta, but you have to integrate over Lorentz invariance momenta. Hopefully, you remember what these guys are. This is the 3 of p over 2 pi to the power of 3 2 e of I. Let me write it down. So it's d of P is integral of d4 of P delta P squared minus M squared, right? 2 point equal to d3P 2 pi 3 to E, right? This is what it was. There's a reason we introduced this notation because we wanted to simplify our lives. All right, so this is, you integrate over these guys. Now imagine you only have only a single particle A, which is at rest, because I can always go to that frame, and a whole bunch of B particles that are moving in this direction. But if particle A was moving with some vector, I'm always gonna go define everything collinear to that vector, right? This particle A could be moving. I'm just gonna pick everything and go to collinear directions, right? Why do I want to do that? Because I want to define the impact parameter. If this guy is at rest, the impact parameter is like this wave packet that's passing this way, right? The center of the wave packet, how far is it from the center of this wave packet? Right? But if they have relative motion, you have to be careful how you define. You always, it's convenient to define everything in collinear, right? Go in a frame that A is basically not moving, right? So this beam that's coming, the total number of incident, the total number of the total number of scattering events is an integral over, if my distribution of B particles are uniform, assume the distribution of particles is uniform, multiplied by the probability of scattering at impact parameter B integrated over the impact parameter B, right? Impact parameter is a two-dimensional thing, right? Because the perpendicular to the collinear direction. It's a perpendicular direction to the direction of propagation of that. The cross section is basically gets rid of this NB, right? So it's just an integral of P of B integrated over over the impact parameter. So now here's something that I want to say. I want to say quickly, and I suggest that you guys go look up the references and think about it, because it's some kinematics. It's a little bit tricky. The initial state of phi A, phi B, I can write it as an integral over Ka and Kb, right? These are the Lorentz invariant integrals. Some wave function phi A and phi B, and Ka, Kb, but it's convenient to put this impact parameter here, e to the power minus IB Kb. This is in the setup that I'm using the collinear variables. Think about why this is sitting there. All right, think about that. But if you get impatient with it, go read Pesky and Schroeder. But I suggest that if you think about it, it's just geometry. This P of B basically is the following thing. So you have to take this, the overlap of this initial wave function with P1 to Pn, square it and integrate over P's, right? All right, so that's what we're gonna do. Here's the wave function squared is like this, right? These PFs are the P1 to Pn. These are the final P's, right? So here's the contribution of one of them. This is the star of it. And here's e to the power of I B KB minus KB and e to the power of I KB bar, because I have two copies of it in PB, right? What I'm doing is I'm doing P of F phi A phi B, right? Squaring it, and right, that's what I'm doing. All right. Putting all of this together, you find that you have to take the probability of PA, PB going to PF. This is the probability, amplitude square. Integrate over final momenta divided by this VA minus VB. This is the part that I also got, I want you guys to think about. This is, again, geometry. There's nothing mind-blowing about this, but you just have to keep track of, you go to discover this factor, you go back to the definition of cross-section I gave you initially, the number of events divided by rho A times rho, divided by rho B, divided by LA, LB, right? You go back to that definition and you see that there is this initial thing, right? That is multiplied by an integral, these covariant integrals over the initial wave functions, and this is just the conservation moment. Good. Questions? I know this is fast, but we don't have all that much time, and the steps of the algebra are pretty straightforward. If there are any steps that are confusing, ask later in the next lectures. All right, so this is the discussion of cross-section. Let's move on to calculating the cross-section. We're going to calculate the cross-section for Compton scattering, E gamma going to E gamma. What we're going to do is we're going to go to the lab frame where this fermion, initial electron, is at rest. So it's M, the momentum is 0, right? And then the photon is omega, omega z hat, right? So it's just propagating the z hat direction, right? The outgoing photon, I can always pick it to be omega prime sine theta cosine theta, right? So I just fix it using an angle theta, and the outgoing fermion will be a generic 4 vector. Well, on shell 4 vector, right? This is just a choice of parameterization. Sorry. What I meant to say is that you always have this, you have to add this to this. This is like this factor, right? It's just conservations. So to obtain the total cross-section, you want to integrate over IT. What is IT? Do you guys remember? It's just M multiplied by this factor, right? You integrate over IT over P prime and K prime momenta, final momenta, right? With the Lorentz invariant measure. This is where you don't know what the final momenta are. You just integrate over them with Lorentz invariant measure. And then there's this initial factor, 1 over 2E, 2EA, 2EB, VA minus VB. Why is that? So VA minus VB you recognize from here, right? The initial wave functions, these guys have D3KA over 2EA and D3KB over 2EB. If I fix KA and KB, I still have the factors of 1 over 2EA and 1 over 2EB, right? So there's this factor, 1 over 2EA, 2EB, VA minus VB. In the coordinates I've chosen, this is 1 over 4M omega. Recall that omega is just the frequency of the photon, incident photon. So you do this algebra. For the sake of time, I've just written it, but I won't use it. I won't explain it much. These are the unshell conditions. These are just basically the unshell conditions, and you do the algebra, you do your integrals. You find that the differential cross-section, they call it theta or phi? Theta. D sigma, D cosine theta, is 1 over 32 pi m squared. M is the mass of the electron. Omega prime over omega squared, 1/4 of sum over m squared. So we had calculated the Compton scattering, 1 over this expression from Compton scattering. Omega prime over omega squared is the only thing that you need to put in next to it with this factor to get the differential cross-section. Recall what omega prime and omega are. Omega is the frequency of the incoming photon. Omega prime is the frequency of the outgoing photon, right? Those are the only variables that are left. All right. You could integrate this. I won't discuss this any further. You could integrate this and no, I made a mistake here. Yeah. Anyway, I probably made a mistake here. I think this is the total cross-section, if I recall correctly, but I don't remember. No, actually, that's not true. That's not true. This is the differential cross-section. All right. So that was one example. Were there questions? I'll have to double check. This equation looks incorrect. I'll have to double check this equation. But you just have to plug in this value we calculated before in these coordinates, right? Now, let's do another sample calculation, but very quickly, I just give you the answers. This is the electron positron going to muon and anti-muon, right? This is the process. And here's what the amplitude is, right? For a photon going this way. Could there be other diagrams? Well, okay, I leave it to you guys. You guys can know this kind of stuff. So we go sit in the center of mass frame, right? So the center of mass frame is going to be, this is another calculation of cross-section, but using, in the previous calculation, we sat in a frame where the electron was at rest and the photon was hitting it, right? Here I'm using a different frame. Sometimes for some calculations, center of mass frame is more convenient, vice versa, depending on the calculation. So this is the, yeah, this is going to be my initial momenta, P and K, right? K is just something, I take initial P of for my particle electron to be in the Z direction, right? Yeah, so that means that my P prime, because of because of I'm the center of mass frame, P prime has to be this, and the final E and K, K and K prime will have to have satisfied these relations. Now, this calculation simplifies quite a lot if you use the approximation that the muon is a lot more massive than electron. You do the calculation, you find that this 1/4 sum over m squared is E4 over E squared. This is the electric charge, right? Over E squared. E squared is the center of mass. The 4E squared is S, is the center of mass energy. So it's S variable, S Mandelstam variables. This is the expression you find. You calculate the differential cross-section. This is what you find. And the total cross-section, you just integrate it and you find this expression. Now, this is something you're going to work out in detail in your homework, but I want to make, the reason I show this is that I want to make a bunch of comments about this. If an electron and positron go through a process like this and produce a pair of leptons, they're called leptons, muons, right? Or other particles, any fermion, any other fermion, antifermion, with the property that their masses are a lot larger than electron, the calculation goes through identically. So this answer is universally true for the process when an electron and positron go and meet each other and they decay to a pair of fermion antifermion. The only thing that, well, okay, I think about the differences. So most of the calculation is identical. How is the calculation different in that case compared to here? Of course, the mass of the fermion will appear here, right? That's the only thing that will come in, right? Do you have any other comments here? Yeah, maybe not. All right. So in summary, what did we discuss today? What we discussed was that we discussed the connection between cross-section and amplitude. The summary of it is something like this. To calculate the cross-section, you have a beam with a particle A, density rho A, of length LA, and surface area A. You have particles that we keep at rest, for instance. Then you have particles of type B with density rho B, length of a beam LB, moving with velocity V. Cross-section, the total number of events is proportional to rho A, rho B, LA, LB, and the A, the area, surface area. So if you take the total number of events and divide by this factor, rho A, rho B, LA, LB, surface area A, you get a cross-section. That's a differential cross-section. It has units of area. And then we basically calculated this. We said that we often define differential cross-section where we fix the final states to have some momenta, right? But these momenta are not all independent. So differential cross-section was somewhat tricky in 2-to-2 scattering. You had theta 5 variables. So we usually write d sigma, d omega, right? Omega is the length element, area element on 2-sphere. We did some sample calculations, but the summary of it was like this. To calculate the total cross-section with fixed initial configurations, you integrate over the final momenta in a Lorentz with a Lorentz covariant weight, right? These are these curly P1s to Pns. And then add to your initial configurations 1 over 2EA, 2EB, VA minus VB, right? So let me summarize it here. To get the cross-section, you integrate over final states with these Lorentz invariant measures, and due to your initial states, you add 1 over 2EA, 2EB, VA minus VB. Inside the integrand and do your integrals. That's how you get the cross-section for a 2-to-n scattering. We also commented on the impact parameter being an intelligent way of organizing our calculation by choosing the collinear variables, labeling momenta of the initial particles in a collinear way. All right, what else did we do? We did some sample calculation. I showed you some sample calculations. Oh, also we talked about the resonances. This is when a single particle that's unstable is propagating, right? We said that if it has lifetime tau, 1 over tau is the total decay rate. And the decay rate shows itself as a pole, as an imaginary part of the pole in the propagator. This was the expression we had, and I justified this using Fourier transform. Then if you just plot the cross-section as a function of energy in the momentum space, basically, or energy if you're just like talking about like 0 + 1 dimensions, right? What you obtain is you see that there are poles in the, there are poles that are associated with stable particles, right? The values of energy would correspond to their masses. When you see bumps, peaks, the height of the peak and the width of the peak are controlled by 2 variables, the mass and the lifetime of that unstable particle. These are called resonances. All right. That wraps up our discussion of scattering and rates, decay rates. Are there any questions? I absolutely recommend reading in detail section 4.5 of Peskin, which goes over this, what I discuss here, slower. And also section 11, I believe 11, right? 11 or 10, I wrote it here, of Srednicki. That has actually a sort of section 11 of Srednicki, which has a different way of thinking about, well, it's not different. It talks about the length of the time period of the beam to motivate cross-section. All right, any questions from what we discussed today, or basically anything up until now? I'll be posting a new homework problem hopefully tomorrow, and homework set tomorrow, problem set tomorrow, and they're starting Thursday. We'll start our discussion of quantization of gauge fields. We'll try to do that minimally and quickly, and then get to anomalous perturbation theory, depending on how much time we'll have. Any last questions? There aren't any. Thank you, guys, and have a nice day. Bye.
Thank you.